Hey, welcome back to Quantum Mechanics for the Working Professional. This is our first problem-solving set, but this is our second problem from that set. We're going to be looking at problem 2 right now. If you haven't yet figured out where the exercises are, they're at the bottom of our lecture, that is to say our lecture notes, on the Stern-Gerlach experiment, section 1. So navigate to the webpage, linked in the show notes below, and then scroll all the way down to the bottom and you'll see exercises. Right now, we're aiming to study problem 2, that is to say, verify equation 5 by explicit computation. And then it gives some rules and blah, 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 blah. So let's take a look at equation 5. That is nothing more than the fact that the probability of finding a silver atom, which is in a two-level system, in the state up is given by this following formula. In other words, can you please compute this formula given the results of problem 1? So let's go ahead and do that. First, remember, the probability of finding a state in, say, up or down configuration depends on what the state itself is in. We have parameterized a generic state, a state which can represent basically any possible physical configuration, by two constants, alpha and beta. We say the state is given by alpha times up and beta times down. What we're interested in is the probability of finding the particle in the state in the up configuration, given that it's in the state psi. And we gave as a definition that as it's the absolute magnitude of up with psi squared divided by psi with psi. In other words, the inner product of psi with itself. In other words, the magnitude of the vector psi. Before we dig into what this number is, I'm going to go ahead and explain to you where this formula came from, because we did actually kind of sweep something under the rug. Given any vector space with a suitable inner product, we can consider the inner product of two vectors, right? We can consider the inner product, say, let u and v be vectors, and we're interested in the inner product u dot v. And it may not surprise you to learn, especially if you have some experience with vector calculus before, that the absolute magnitude of u dot v is always going to be less than the absolute magnitude of u times the absolute magnitude of v. In other words, it's always going to be a projection of u against each other, and the biggest it could ever possibly be is the absolute value of both of those two vectors. In other words, mathematically speaking, the mod square of u dot v is always going to be less than or equal to the mod square of vector u times the mod square of vector v. The mod square being, the absolute magnitude, the distance, however you want to frame it, to that concept of v dot v times u dot u. All right, so let me write that out explicitly. U dot u times v dot v. This is called the Cauchy-Schwarz Inequality, and it is a fundamental property of basically any inner product that you can invent for spaces like this that would help you do calculus. So it's just a fact of life, if you like. So what we're going to be doing here is mapping these u's and v's onto the vectors that we're already familiar with. So for our case, we were interested in computing the absolute magnitude squared, right, of our vector up with psi, right? So the absolute magnitude square of that then, according to the Cauchy-Schwarz inequality, is going to be less than or equal to up with up times psi with psi. Up with up, of course, is the magnitude of the up vector, the modulus square of the up vector, and psi with psi is the modulus square of the psi vector. Now, what I swept under the rug was the fact that up with up is actually equal to 1, as we computed last time, but I'm just going to let it hang around here for a while. In fact, I'm going to divide by a positive number, both of which are positive. I'm going to divide by both of these magnitude squares, these ups with ups, and we'll find that the modulus square of up with psi divided by up with up and psi with psi is always less than or equal to 1 by the Cauchy-Schwarz inequality, right? So this number is always, in other words, the projection of the state 1 onto the state psi, how much upness there is in the generic state psi, is always going to be less than or equal to some junk. But if we divide out by all that junk, the projection of the state up on the state psi divided by all that junk is less than or equal to 1. So that codifies our concept of a probability theory. In other words, there will always be a probability of at least 0 and at most 100%. Now, again, we observe that up with up is actually equal to 1. And so that's where we got our concept of the probability of finding the state in the up configuration being given there. Alternatively, we can ask the question, what is the state, what is the probability of finding the state in the down configuration? And that just means we need to project the state psi with down, right? And down with down, again, as we saw at the last problem, has a magnitude 1 as well. So this leads us to one final thing that I'm gonna come to before I explicitly do all these calculations. And that is, given some state, random state, psi, and some other reference state, phi, what is the probability of finding psi in the state phi, right? Hopefully by now you can remember the Cauchy-Schwarz inequality and do this for yourself. So the probability of finding the state in the configuration psi is, in the configuration phi, is the magnitude of phi with psi, whole quantity squared, divided by the magnitude of phi times the magnitude of psi. Very symmetric looking, right? But this, again, just comes from that simple inequality because this is a number between 0 and 1. And effectively what it's capturing is the projection, the percent of, state phi that happens to be in state psi. And of course, because we're talking about absolute value squares, you can think of that from either perspective. You can think of it from phi's perspective. What's the probability of finding the state psi in the quantum state phi, or vice versa? Okay, now let's do the actual computation. Good. So we know from last time that up with up is equal to 1, and up with down is equal to down with up is equal to 0. Similarly, we know that down with down is equal to 1. So the quantity up with psi is equal to the quantity up with alpha times up plus beta times down. Right? So this is just simply up with alpha times up with beta times down. But we know that up with down is 0, so this is just alpha. And so, of course, the absolute magnitude of alpha is just the absolute magnitude of alpha. Right? Easy enough. So the only thing that we really have to compute now is psi with psi. So let's do that. Psi with psi is the same thing as alpha up plus beta down, now working with the bra vectors, right, or the row vectors, that whole thing acting on psi. So this is hopefully familiar right now. We just have alpha times up with psi plus beta times down with psi, but we already know what up with psi is. That's just alpha, and hopefully, similarly, it's not too much of a stretch for you to figure out that down with psi is just beta. So that's alpha squared plus beta squared. And, again, we'll get to the whole complex number idea in the future, but for now, these are real numbers, so they're equal to their absolute magnitude. So in other words, alpha squared plus mod beta squared. Great, so the probability then of finding the state in the up configuration is just mod alpha squared over mod alpha squared plus mod beta squared. Similarly, for the case of the down configuration, we just simply exchange the up with down in the numerator and find beta squared divided by alpha squared plus beta squared, which gives us the nice interpretation, right, that if we say, hey, we've got two levels, we've got a two-level system, what's the sum of the probabilities for looking for the state in the up configuration and the down configuration? And of course, in this particular instance, alpha squared plus beta squared divided by alpha squared plus beta squared. In other words, the probability of finding the particle in the up state plus the probability of finding the particle in the down state is equal to 1. In other words, it's a two-level system, and so it's got to be in either up or down configuration. Great. Okay, not so bad, huh? Hopefully it's not too annoying to go a little bit out of order, but it just seems much better now from a communicating the solutions perspective to solve problem 7. I like the idea of mixing up the ideas in the different problem sets for you to kind of execute on your own. But in terms of answering the solutions, the answer to problem 7, exercise 7, stems directly from our discussions of problems 1 and 2. So I thought we might as well just answer it now. So for problem 7, you're asked to verify that the physical consequences of multiplying a generic state vector psi by some positive real constant, or any real constant really, c, are nil, nothing. In other words, the state psi is identical to the state c psi, where c is a real number. Okay, so let's see why that would be. So again, remember that our state psi, our generic state in a quantum two-level system, up and down, right, has alpha in the up direction and beta in the down direction. And what we're interested in here is saying, okay, I'm going to multiply everything by c. So c psi is given by c times alpha up plus c times beta down. So let's call this new state psi prime. Okay, so what we're interested in showing is that the probability of finding whatever, right, say up with psi prime, is the same as finding the probability up with psi. In other words, what we're trying to show is that the probability prime given by the quantity up with psi prime is equal to the probability of finding the particle in the state psi up. In other words, it hasn't changed the physical reality whatsoever. Okay, so let's go ahead and do that. So just from our definitions, we already see that multiplying the entire state vector psi by a constant c, a real constant, just amounts to multiplying the components. So in other words, alpha goes to c times alpha and beta goes to c times beta. Since the probability that we discussed last time of finding the particle in the up state is given by mod alpha squared divided by mod beta squared plus mod alpha squared, what you actually end up doing is just multiplying by c on the numerator and the denominator, right? Or I should say c squared. So that's just c squared alpha squared times c squared alpha squared plus c squared times beta squared. And you just cancel all the c squareds out, and you end up with exactly the same number that you started with. Piece of cake. Similarly, for the down state, beta squared over alpha squared plus beta squared, all the c's cancel again. So once again, no physical impact whatsoever from multiplying a state vector psi by some real constant c. A lot of folks have a lot of complicated intuition for dealing with that kind of thing. They might say something along the lines of, we're interested only in rays in the Hilbert space of quantum states, or we're talking about a projective space of quantum states, a bunch of other junk that you're going to see on Wikipedia, for example. And that's fine. Those fancy terminologies in mathematics, you can define it however you want. But as a physicist, my instinct is to define the thing that makes the most physical sense. So from my perspective, what we're going to end up doing moving forward, and we'll discuss this again in future lectures, is that we're going to choose a constant c such that the inner product of a quantum state with itself is always equal to 1. In other words, we're using that degree of freedom, that extra physical reality degree of freedom, to just fix the magnitude of the quantum state, of any quantum state, psi, to be normalized. Why? So then we can really think of the quantum wave function, or that quantum state, that state vector, as a probability distribution in its own right. So we don't have to carry around all these things and divide by. So on the one hand, it's convenient mathematically, because then we can use the Cauchy-Schwarz inequality without having to divide anything on the right-hand side, because everything's equal to 1 anyway. And from a kind of physical interpretation perspective, we're just thinking of the quantum state as probability distributions in their own right. So that's why. It is worth pointing out in this case, again, we haven't discussed complex numbers yet, but it's important that c is a real number. For those of you who know about complex numbers, if c were a complex number, we could split c into its polar, its magnitude, its, the magnitude r, the radial component, and the phase, angle, direction. And as it turns out, the phase matters a lot. And the phase is a really physical, observable thing. This is the Aharonov-Bohm effect, and we will talk about that later. But suffice it to say, it's required for our discussion here that we're talking about the magnitude of the vector. And the magnitude means that little number c that we multiply our states psi with is a real number. That's all. Okay, great. That's all for this round of problems. In the next round of problems, we're going to look at, we're going to look more deeply at different bases of quantum states. Great. Okay, so until then, see you next time.